This video will contain 3 examples using conservation of energy to solve problems. The first problem is a conceptual one. A skateboard with initial speed v sub 0 rolls towards a ramp that has a shape of a quarter circle. It rolls up the ramp to a height h. If the initial speed were doubled, how high would it roll up the ramp? Please take a moment, pause the video, choose an answer of your own. Be sure you can articulate your reasoning for that choice. The correct answer is answer D, 4 times h. Our explanation for this answer is that we are actually comparing 2 different situations. In situation 1, we begin with an initial kinetic energy of 1/2 mv0 squared, and equate that to a final potential energy of mgh. We can do this because the initial situation has no potential energy, and the final situation has no kinetic energy. In the second situation, we are actually beginning with a totally different initial speed, twice v0. Our conservation of energy equation looks the same, but our initial kinetic energy is larger by a factor of 4. Therefore, our final potential energy is larger by a factor of 4 as well. The final potential energy can only be larger by a factor of 4 if it is coming from a height that is larger by a factor of 4 also. Therefore, our answer must be 4 times the height in situation 1. Our second example will be an Atwood machine. It consists of 2 masses connected by a string which runs over the top of a frictionless pulley. You may remember solving this type of problem using accelerations and forces on an earlier homework assignment. Let's ask a question that we can easily solve with conservation of energy. Say that both masses begin at rest at an equal level. They're then let go, and one of the masses slides up while the other one slides down. Let's assume for the purpose of the diagram that mass 2 is heavier and mass 1 moves up after it's released by an amount delta y, and mass 2 moves down by an amount negative delta y. The 2 masses have to move in unison because the string has a constant length. Approaching this in terms of conservation of energy, we want to think again about an initial configuration, another configuration, or the final configuration, and what are the velocities, speeds, and coordinates at both points. In this initial configuration, we've started with the masses both at the same height. So let's call that y equals 0. That seems like an okay choice. And both masses begin at rest. So their velocities, v1 and v2 in the initial state, are both 0. Both vertical coordinates, y10 0 and y20 0, are also both 0. So this is kind of a fun example because the initial energy is 0. Well, we might think, oh, if it's got no energy, then it can't do anything at all. But let's see what happens. Okay, think about the final situation. What will change? Mass 1 will move up, so it will gain some potential energy. Mass 2 will move down, so it will lose some potential energy. The potential energy of mass 2 will actually become negative. Both masses will begin moving, and they'll have to move at the same speed because of the string. Can't stretch or shrink. So for the purposes of the diagram, let's again say mass 1 moves up, mass 2 moves down. That means at the final situation, we'll have mass 1 moving up at a speed v sub f, and mass 2 moving down at a speed v sub f. The y-coordinates will change by delta y. And our final energy will have a different expression because these things are not all 0 now. So I have 4 terms: the kinetic energy of mass 1, kinetic energy of mass 2. Because velocity is squared, it doesn't matter that there's a negative sign here. It gets eliminated when I square that VF. The potential energy of mass 1 and the potential energy of mass 2. I've taken the negative sign from the V2F and put it in front of the whole expression. Before I start to solve this out, I'm going to simplify the expression for EF a little bit. Notice that there's some common factors in this first term, the 1/2 and the VF squared. So I'll write those by themselves outside of a parentheses. In the second term, there's also some common factors. The G and the delta Y. Now if I want to relate VF and delta Y to each other, I can do so by using the principle of conservation of energy. There is no friction in this system, so therefore the final energy EF and the initial energy E0 are equal. E0 was 0, so EF is 0 at all times. So this is the equation we get for conservation of energy. Now, depending on the goal here, we could solve for any one of these variables. I'm going to arrange it to solve for VF to see what that looks like. So we have to take the square root of a lot of stuff. We've got a fraction involving the difference in mass divided by the sum in mass times twice the acceleration of gravity times the difference in height y. And whenever we have a square root, we have to be concerned a little bit that the things underneath the square root aren't negative. We have a difference here, m2 minus m1. And if we look at that, we could see, oh, if m2 was less than m1, this would be negative and we'd have a big problem, right? The resolution to that is the fact that delta y is also inside of here. So in our diagram, we drew it as if m2 is heavier. So this difference would be positive, and the delta y would be positive. So then we have a positive times a positive, and we're okay. The variables don't know, though, that this specific drawing is what we had in mind. If we plugged in an M1 that was larger than M2, we would get a negative sign here. And if we persisted in assuming that delta y was positive, we would have an invalid square root. The final velocity has to be a real number. So the resolution to that is that if M1 is larger, then the delta y must be negative. If M1 is larger, M1 moves down. That's good. That makes sense. Okay. So again, we find that in cases of energy, we have a very simple mathematics to go through, just writing out the expressions and setting them equal to each other. But we do have to put a little thought into the direction of quantities, the direction of velocities, and the direction of displacements. Now let's solve an example problem where there are two types of potential energy involved. The elevator has a mass of 500 kilograms and an initial height above the top of the spring of 10 meters. The spring has a spring constant of 30,000 newtons per meter. The final configuration requires a bit of context. As the elevator falls down, it will increase in speed until it hits the spring. The spring will then produce an upwards force which will ultimately stop the elevator at some point. Therefore, our final position is somewhat below the reference level at the top of the spring. The spring is compressed. And YF would have some negative value. In both situations, the velocity is 0. In the final one, it's 0 because the spring has momentarily stopped the motion of the elevator. Right afterwards, the spring will push the elevator back up. Initially, the velocity is 0 because the object began from rest. Let's now write down the expression for the total mechanical energy in each situation, taking into account that there is now a gravitational potential energy and a spring potential energy. In the initial situation, the kinetic energy is 0, so I haven't written it. The gravitational potential energy is m times g times the initial height, y0, which is 10 meters. The spring is not compressed at all, so its initial potential energy is 0. The spring only begins to store potential energy once the elevator moves below the top of its uncompressed length. In the final situation, we have gravitational potential energy and spring potential energy. Gravitational energy will be negative because YF is below our reference level. The potential energy of the spring will be positive even though YF is negative because YF gets squared. A spring stores positive energy whether it's compressed or extended. To solve for YF, we will use the principle of conservation of energy. The final energy and initial energy must be the same, since there are only conservative forces. Notice that YF appears to the first power and to the second power, and there is a constant term. So to solve for YF, we will have to use quadratic formula. Before doing that, I'm going to simplify a bit to make the quadratic formula less messy when I use it. I've moved the YF squared term to the front and eliminated its coefficients by multiplying the whole equation by 2 and dividing the whole equation by k. We will then use the quadratic formula. Simplifying this as much as we can, we obtain these are our two solutions for the final position of the elevator when it stops momentarily at the full compression of the spring. We expected this value of YF to be negative because the elevator is below the initial height of the spring. We have a negative term here, but the second one can be plus or minus. Both will solve the conservation of energy equation. We need to think about which one to choose. If we look at what's inside of the square root, we see that it is definitely larger than this term. These terms here are positive. So the square root itself is larger than mg over k. So I'm taking a negative term and I'm adding or subtracting something which is larger than it in absolute value. That means that the plus sign choice would result in a positive value of yf, and the negative sign choice would result in a negative value for yf. Given the context, we should choose the minus root. Plugging in the values that we were given at the start of the problem, we will come up with a value of yf of negative 1.98 meters.